In this video, we are going to derive the expressions for the adiabatic expansion process. Now, we're going to use the first law equation. We know that from the first law, dq is equal to du plus dw. Now, under an adiabatic expression or an adiabatic condition, we have that dq is equal to 0. So this will be 0. That is equal to du plus dw. Now, from extrapolations, we know that du is the same thing as ncv dt. And we also know that dw is the same thing as pdv. So what I'm going to do, I would actually take this as well as this and replace du and dw with them. So that is going to give 0, and here we're going to have an ncv dt, and here we're going to have a pdv. Now, next up, we know that from the ideal gas equations, we should have PV and that be equal to nRT. Now, we know that from the previous equation, we have a P within the expression for the work done. So I could well express the ideal gas equation in terms of V. Well, that should be in terms of P, rather. So this is going to be P, and that is going to be equal to nRT divided by V. Now next up, I need to take this and plug it in this equation. So let us do that. That is going to be 0, and this will be ncv dt plus nRT divided by V multiplied by dV. Now the next thing I'm going to do, I would actually factor out or divide through rather by n. So that is going to leave us with a 0, and here we're going to have a CV. This is a CV plus an RT dV that is divided by V. Now notice from this resulting equation that we do have dt on one part of the left hand side. This should be the right hand side. We have a dt here, but we do not have a t with it, whereas we have a dv here and a v. So what we are going to do, we're going to take this t to the other side. How can we do that? Now that is basically by multiplying both sides with 1 over t. So if I multiply 1 over t with a 0, that is going to give us a 0. And if I multiply 1 over t with this form, I'm actually going to have cv dt divided by t. Now here I'm going to have 1 over t multiplied by this stuff. That is going to help me to cancel t's out. So that leaves us, that leaves us with an r dv divided by v. Now next up, I'm going to take r. Well, instead of doing that, I'm actually going to take cv and take it to this other side. Now how can I do that? That should come off pretty much in a similar way as I did it in the previous case. So I'm also going to multiply through by the reciprocal of cv. On this side, that's pretty much going to give us a 0. And here we're going to have this. That is a cv cancelling out. So that gives us a dt divided by t. And here we're going to have an r divided by cv. And this is dv over v. So that is actually what we have. Now the next thing I'm going to do, I would actually integrate both sides of this resulting equation. So let us try to do that. That will be integral 0, and on this side we're going to have integral dt over t plus integral r divided by cv dv over v. So that is what you have there. Now if we wanted to integrate it 0, what is that going to give? So naturally this should give a constant. And on this side, we have a dt divided by t. If you wanted to integrate this, this is actually going to give you an ln t. Now here we're going to have this stuff come out because we have R to be the universal gas constant, and C sub V, that is actually the heat capacity at constant volume. So that is also a constant. And in this case, the two are constant. So since they are multiplied with this variable, I'm actually going to take them out and work the integration on this stuff. So that is going to be R divided by C sub V, and that will be integral this, which should give us an ln V. Bear in mind we already have integral dt divided by t. That gave us our ln t. So if you have integral dv divided by v, that is going to give you an ln v. Now, bear in mind if we have Cp minus Cv, that is equal to the universal gas constant. This is the heat capacity at constant pressure, and this is the heat capacity at constant volume. If I divide it through by C sub V, that is going to have this equation change to this form. So here we're going to have a Cp over C sub V, and on this side I'm going to have an R divided by C sub V plus 1. So this part, this is actually a gamma ratio. If you had Cp divided by Cv, that is the same thing as a gamma ratio, and that will be equal to 1 plus R divided by C sub V. Now you need to hold this at the back. We're going to use it in a little while. Now, coming back to this form, this equation, we have that this form could actually go to this other side. So let us try to do that. That is going to be a constant, and this will be equal to ln t plus ln v raised to the power of r divided by c sub v. Now from the laws of logarithm, we know that these have a similar basis, so we could actually bring them together, and that is going to give us some very useful. So this is going to be an ln t multiplied by v raised to the power of r divided by c sub v. Now we know that ln is the same thing as log to the base e. So that will be log to the base e of t multiplied by v raised to the power of r divided by c sub v. And this is equal to a constant. This is a logarithmic equation. How can we change it from a logarithmic equation into an indicial? So I need to raise the exponential to the power of this constant. That will be equal to this stuff. So that is e raised to the power of the constant, and that is equal to this stuff. So this is what we should have. We have e to the constant, and this is equal to t multiplied by v, and that will be raised to the power of r divided by c sub v. Now, if you have an exponential, which of course that is 2.72, and a constant, that might be any number, but basically this is a constant raised to the power of another constant. So that should basically take us back to a constant. So this will be a constant. And this is equal to t multiplied by v raised to the power of c sub raised to the power of r divided by c sub v. Now there is one other thing that we need to do here before we go on. From the ideal gas equation, we have that PV is equal to nRT. That is what we have, right? So this is what we're going to do. We know that if you carried P and V and divided it by T, that will be equal to a constant, right? Now, from this equation, we have that T is equal to PV divided by NR. So that is what I'm going to do. I would actually use this equation and plug it back into the previous equation we formed, this one. So in this case, T will be equal to P multiplied by V divided by NR. So here now we should have a constant, and that is equal to t, which in this case is now PV divided by n r, and this will be multiplied by v raised to the power of r divided by c sub v. Now we know this v is raised to the power of 1. So this is going to be a constant. Now I'm just going to write it as a k. That represents a constant. And here we have a p. This is divided by n multiplied by r. And this is v raised to the power of 1 multiplied by v raised to the power of r divided by c sub v. Now from the laws of indices, we know that these two powers could be added because we have similar bases. So this is going to be r, well, that should be v raised to the power of 1 plus r divided by c sub v. Now this actually should seem alike, or this actually is the same thing as we had written out here. We said that 1 plus r divided by c sub v is the same thing as the gamma ratio. So instead of writing that bulky stuff, we are actually going to change it and replace this form with the gamma. So k is equal to p multiplied by v raised to the power of gamma, and this is divided by nr. Here now we know that nr multiplied by k will form, and on the other side we're going to have p multiplied by v raised to the power of gamma. Now this are constants, and if you multiply a constant with a constant, that pretty much is still going to give you another constant. So all these ends up in a constant. So that is PV raised to the power of gamma. This is the first representation, the first form of the adiabatic expansion equation. PV raised to the power of gamma is actually equal to constant. Now we could actually form two other forms of it. That is still by the use of the ideal gas equation. And before we go there, we know that this means if you have a P1, V1, and that equal to the power of gamma, that is equal to P2, V2, and that equal to, well, that raised to the power of gamma. So this also works. Now let us try to find out what the other expressions are going to be. So we know that from the ideal gas equation, we should have PV and that equal to nRT. Now basically you know this is a constant. So we really don't need to worry about that, but we're actually going to use it in the derivations. Later on they're actually going to get eliminated, so you don't really need to bother about that. Now let's say in this case we try to take out a p and replace it with a t. So p in this case could be nRT divided by v. And so therefore we need to take this and plug it into this equation as p. And so k will be equal to nRT divided by v. That is multiplied by v raised to the power of gamma. So this is equal to nRT, and this will be v raised to the power of gamma divided by v. Here now we could take nr to the other side by dividing. That should give us k divided by nr, and here we're going to have a t multiplied by v raised to the power of gamma minus 1, because we have this to the power of 1 as its index. So that should give you a gamma minus 1 from the laws of indices. Now here we also have constants, and these all reduce to a constant. So this is going to be t multiplied by v raised to the power of gamma minus 1. That is the second equation for the adiabatic expansion process. So we have k is equal to tv raised to the power of gamma minus 1. So you know what that means, right? That is going to be t1 v1 raised to the power of gamma minus 1, and this will be equal to t2 v2 raised to the power of gamma minus 1. Now, can we find any other one? Of course we can. There is one more expression that we need to write, which is actually in terms of t and p. So let us try to make the v the subject from the ideal gas equation. V will be equal to nRT divided by P. Now let us plug that back into the original equation. So K will be equal to P multiplied by V, which in this case is nRT divided by P, this all raised to the power of a gamma. Now you know this should actually change to something like this. Now I know I could well wipe this out because this is not so useful. If you know this, then you could form any equation from it. I also need to wipe this stuff out. Yep. Now this also goes. So we have the other K that is equal to TV raised to the power of gamma minus 1. So I can wipe this also out. So from here we have K is equal to P raised to the power of gamma multiplied by NR all raised to the power of gamma. And this is T raised to the power of gamma. And this will be divided by P raised to the power of gamma. Now this could go to the other side as we divide through by NR raised to the power of gamma, or multiply through by the reciprocal of the form. So that basically should cancel out on the right hand side and come over to the left hand side. So this part should get cancelled. And here we should have K divided by NR raised to the power of gamma. And here we have P raised to the power of 1 divided by P raised to the power of gamma. And we have T raised to the power of gamma. We know that this form should give us a constant because all these forms, they're actually constants. So this is going to be a constant. And on this other side, we should have a P raised to the power of 1 minus the gamma because this is actually the powers of the base P, standing for pressure. We have T raised to the power of gamma. So this will be the third and last form of equation from the adiabatic expansion process. So these are the three equations that you need to know. If you have this, you could always increase them. If you have P raised to the power of 1 minus gamma multiplied by T raised to the power of gamma, and this was equal to a constant, you could well increase it. That is, you could have P1 and T1, and you could also have a P2, 1 minus gamma, T raised to the power of gamma, 2. So if you have that, that could still work. So this is pretty much it. The equations for the adiabatic expansion process.